Quantum mechanics gets weirder as we go to smaller sizes and higher energies. It's strange enough for atoms, but positively bizarre when we get to the atomic nucleus. And today we are going nuclear as we dive into the weird world of quantum chromodynamics. As you know, atoms consist of a nucleus of protons and neutrons surrounded by electrons. Those electrons are held in their orbitals by the electromagnetic force. Opposite charges attract, and so the negatively charged electrons are attracted by the positively charged protons. But in electromagnetism, like charges repel. So how does that work with heavier elements? There, multiple electrons repel each other, but fortunately are spread out enough to not disturb each other too much. The protons, on the other hand, are packed together in the nucleus as tightly as any matter in the universe. The repulsive force between them due to electromagnetism is absolutely enormous. So, how does the nucleus stay together? Well, it's due to an even stronger force, namely the strong nuclear force. But if the strong force is so strong, why is it confined to the atomic nucleus? The answers to all of these questions lie in the complex behavior of quarks and gluons via the rules of quantum chromodynamics. Our lead to understanding the strong force came in the 1940s when we switched on our first particle accelerators and started to detect a veritable zoo of new particles. As physicists tried to understand the aptly named particle zoo, certain peculiar relationships were observed. In particular, Maribel and others realized that the way these particles were created in particle collisions suggested the existence of a new conserved quantity that they named strangeness. And strangeness was strange indeed. Gell-Mann and Yuval Ne'eman noticed that if you arrange particles according to their strangeness and their electric charge, they fall into geometric patterns like this hexagon with 8 particles or this triangle with 10. This is known as the eightfold way, and it's like a periodic table, but for particles. Before too long, it was realized that the particles of the particle zoo were not elementary. They were made of smaller particles still, and those particles are quarks. It turns out that location on these shapes represents the quark content of the particle. Strangeness just turned out to represent how many strange quarks are present. By the way, these particles of multiple quarks are now called hadrons. Describing hadrons as groups of quarks explains the eightfold way, but it also introduces a new problem. To understand the problem, I want you to imagine that you're at a fancy party and you're wearing your brand new pretty dress, or jacket or jumpsuit or whatever, I don't judge. Anyway, someone shows up wearing the exact same outfit. Mortifying, right? Well, it turns out that nature also has its fashion police. For the class of particles called fermions, no more than one particle can wear the same dress or occupy the same quantum state. That includes electrons, quarks, and many of the particles that are composed of quarks. This restriction is known as the Pauli exclusion principle. One consequence of this is that no 2 electrons can occupy the same energy level in an atom. Well, slight correction. Electron orbitals can contain 2 electrons, but that's because those electrons can have different spin states. It's like they have the same dress but in different colors, and we made an episode all about that. Okay, so how does this apply to quarks? Let's look at the Omega baryon. It's made of 3 strange quarks. Well, in reality, 3 valence strange quarks, 3 quarks in the top energy level. There's a lot happening under the hood. Now, there must be something different between these quarks in order for them to comply with the exclusion principle. It can't be spin, because with 3 particles and only 2 possible spin states, 2 will always have the same spin. The only solution is that there must be some other property making them different, and that property must have 3 different possible values. With electromagnetism, you have one type of charge, which can be positive or negative. With the strong force, you have 3 charge types. If our omega particles quarks are going to wear the same dress, they better be different colors. In fact, we label these 3 strong force charges with the colors red, green, and blue. And this colorful convention led to the naming of our science of strong force interactions, quantum chromodynamics. Of course, the quarks aren't literally coloured, but as we'll see in a bit, there is a very good reason scientists thought about colours when naming this property. If we have different charges, then we have a potential for attractive forces. We need this attraction to hold quarks together in nucleons, and nucleons together in the atomic nucleus. And that attractive force needs to be stronger than the repulsive electromagnetism while still vanishing outside the atomic nucleus. How can that work? There's another weird behaviour of the hadrons that'll help us answer this question. It turns out that all of these particles are made of 2 or 3 quarks. It's possible to briefly create larger combinations in particle colliders, but not in nature. And most importantly, we never see lone quarks except in very particular circumstances. Let's lay out what we need from our strong force for all of this to work. The force is similar to electromagnetism in some respects, but it's very different in others. Electrically charged particles interact with each other via the electromagnetic field. We can think of each charged particle as generating a constant buzz of virtual photons around it, forming what we think of as its EM field. That buzz weakens the further you get from the particle. So an electron bound to an atomic nucleus will feel less force from the nucleus at larger orbitals. The further the electron gets from the nucleus, the more easily it can escape. Assuming the strong force works roughly the same way, we need a field to mediate it. And that field should have its own particles. We call those particles gluons. A pair of quarks bound into, say, a pion. Connected by a gluon field, also describable as a constant exchange of virtual gluons. But this field looks very different to the electromagnetic field around the nucleus. For one thing, it does not weaken as the quarks are moved further apart. Instead of forming a fading gradient of field strength, quark pairs are connected by a thread of gluon field called a flux tube. As quarks are separated, the thread doesn't weaken like the EM field does. The flux tube has a tension, and just like a stretched elastic band, the more you stretch the flux tube, the more energy it holds. At a certain point, the tube will snap, but only when exactly enough energy has been built up to create a new pair of quarks. Now, each of the original quarks is partnered with one of the new quarks, forming 2 new pions from the single pion. And the same would happen with any of the other particles made of quarks. If you want to break them apart, you just end up forming new particles. So quarks never end up alone except in the most extreme energies. With enough energy, like in the very early universe or at the impact point in a large particle collider, space gets sort of saturated so that new quarks can't be formed. That allows quarks to move freely in a state of matter known as a quark-gluon plasma. This behavior of the gluon field explains why we only see quarks in groups, but we still need one more puzzle piece to explain why the strong force is never seen outside the nucleus. The answer is something called color confinement. It ensures that color charge is mostly only felt inside the hadrons. There are 2 parts to this. The first one is that quarks always get together in groups that are color neutral, and the second is that there are no neutral gluons. To understand the first one, we have to see how the strong force is similar to electromagnetism. Let's say we have a proton and an electron. Their electric charges attract and they form a neutral hydrogen atom. This is what electrical charges do. They attract each other until the electrical fields cancel out. And that's why everything around you is electrically neutral. You would have to get really close to an atom to feel the positive electric field of the nucleus or the negative electric field of the electrons. Something similar happens with color charges. They also attract each other until they form groups that have neutral color. This makes sense when we have 2 quarks. They have opposite color charges so they cancel out. For example, the quarks of a pion could be red and anti-red. But what happens when we have 3 quarks? How do they cancel out? Maybe they didn't teach you this equation in school, but it turns out that red plus blue plus green equals 0. That same formula tells us, for example, that blue equals minus red minus green. In fact, each color charge is equal to the negative sum of the other 2. This may sound crazy, but it may not sound so crazy if you are a photographer or a graphic designer, because this is exactly how the RGB system works. Your screen can't make this color, or this one, or even this pure white. All it can do is combinations of red, green, and blue. White is what you get when you combine all three in equal quantities. That's your red plus green plus blue equals 0. And yellow is just red plus green, which means that yellow is minus blue, or anti-blue if we're using the language of quantum chromodynamics. The mathematics used to describe this system just happens to be the same as the mathematics that describes the behavior of the charges in the strong force. It has three primary colors like the three charges of the strong force, each of which can be positive or negative and transform into each other additively in the same way, or cancel out to neutrality. This apparent coincidence is why physicists called them color charges in the first place. But it's not as weird a coincidence as you might think, and I will tell you why shortly. First, let's get to the other requirements for color confinement. No neutral gluons. And for this, we need to compare the strong force and electromagnetism once again. Electrically neutral objects cannot feel electrostatic attraction, but they can certainly feel magnetism. You see it all the time when a piece of neutral metal is attracted to a magnet which is itself also neutral. This is possible because the mediating particle of electromagnetism, the photon, is itself electrically neutral. That means photons can interact with objects without affecting their electric charge, and thus neutral objects can interact with magnetic fields. There is a strong interaction similar to magnetism called chromomagnetism, but that's where the similarities end, because gluons are not neutral like photons. Gluons carry color charge. In fact, they carry two charges at the same time, a positive and a negative of different colors, or more accurately, a superposition of multiple positive negative colors, and they cannot be color neutral. This means gluons are unable to interact with neutral particles like the combinations of quarks that form the hadrons. If they could, hadrons would be able to feel chromomagnetism, which could make the strong force a long-range force, and that would probably be bad, or at the very least very different from the universe that we know. Gluons can carry many different combinations of colors and are always in a superposition of multiple combos. For example, a gluon could be a combination of green anti-blue and blue anti-green, which we write like this. Such a gluon might turn a blue quark green or a green quark blue. Sometimes we even have to consider three possibilities, like a red anti-red plus blue anti-blue minus 2 times green anti-green. This last one looks color neutral because each of those three combos appears to cancel out, but it's not really neutral because the probability of the green interaction is double the other ones. It turns out that we can express the state of any gluon as a combination of only 8 gluons. 6 of them have color charge, and 2 of them are neutral but unbalanced. So does this look familiar? It is the eightfold way from earlier, and in fact, we can also use it for the 8 colors of RGB. Red, blue, and green, plus anti-red, anti-blue, anti-green, or as we know them better, cyan, yellow, and magenta, and then black and white at the center. The position of each object on the hexagon tells you how much they have of a certain type of quark, a certain color charge, or a certain amount of actual color. The reason this pattern arises in so many different places is a question of symmetry. Whenever you have a combination of 3 degrees of freedom in groups of 3, and 2 of those combinations are neutral, like the black and white, you get this mathematical structure. Its name is Special Unitary Group of Order 3, but we're all friends here, so we can call it SU3. This symmetry is baked into the laws of physics, and there it manifests as the strong force. But SU3 appears in many other contexts, like in the behavior of the color receptors in our eyes. We have 3 color receptors, and our brains use the SU3 symmetry group to combine the input from those receptors into our subjective sense of color. When we build a screen to display only red, blue, and green pixels, we're manipulating the way our brain interprets combinations of these colors. But this isn't the only way biology does this. Birds have 4 color receptors, dogs have 2, and the mantis shrimp has 16. By chance, we have the same number as there are degrees of freedom in the strong force color charge. Okay, so this was a very brief introduction to chromodynamics and the strong force. As you can imagine, there is a lot more to it. And so, in future episodes, we'll dive deeper into the strongest force in all of spacetime. Before we get to comments, we wanted to let you history lovers in our audience know about a new series from PBS called The Bigger Picture. Hosted by Professor Vincent Brown, it's a show that looks at famous photographs by examining how they happened and exploring the historical context around them. They recently did an episode on the iconic blue marble photograph of Earth and the legend of how NASA changed the Apollo 17 mission to capture it. Links are in the description, and tell them, politely, that Spacetime sends you. We may not be a big budget network production, which is good because what big network would let us go as deep as we do? But even so, this show does take money to create, and our supporters on Patreon cover a good chunk of that. So thanks to all of you who support us there. Today's special Patreon shout out goes to Gautam Shine, who's supporting us at the Big Bang level. Gautam, if this show is a hadron, then your support is a gluon flux tube. It's the unbreakable bond that keeps our quarks together. I'm not sure that the quarks are actually anything in this metaphor, and really it's probably a good idea not to think too hard about it, but the comparison of your help to the strongest force in nature is clearly apt, so we thank you. Today we're doing comment responses for the last 2 episodes. There was the one on lattice QCD, where we talked about simulating the atomic nucleus, and then the one on quintessence, one of the leading ideas for how dark energy might behave. Starting with lattice QCD, although the questions are really more generally about particle physics. Jeremiah Young asks whether relativistic time dilation occurs due to the thermal motion of particles. In other words, if heating something means the particles are moving faster, does time slow down for those particles? Well, the answer is yes, but the effect isn't noticeable until a few billion Kelvin in temperature. Matter at that temperature forms a relativistic plasma, and we can produce such matter in our labs, and we see it in cataclysmic astrophysical events, the various explosions and collisions that we see out there. We don't see these plasmas actually freeze in time, just that their spectrum is changed a bit from the typical thermal spectrum of hot matter. There's also other weird stuff like the fact that there's enough kinetic energy in this matter to cause spontaneous particle-antiparticle creation. In general, it's a very difficult state of matter to do calculations on. John Jarmarket and Gabrielle Monteiro de Castro both asked the same question. If virtual particles don't actually exist but instead are a calculation tool to describe fluctuating quantum fields, what does that mean for Hawking radiation? After all, Hawking radiation is sometimes portrayed as virtual antiparticle pairs being separated by a black hole event horizon. Well, the answer is that the story about separation of virtual particles by an event horizon is really just meant to be an intuitive picture of what's happening, and has only a loose connection to the reality. Hawking originally derived his radiation by calculating the disturbances on the quantum fields due to the appearance of an event horizon. Those fields normally have positive and negative frequency modes that cancel each other out to leave a vacuum, but the event horizon changes the balance of these modes, causing imperfect cancelling, which looks like particles being radiated away by a black hole. I suggest searching for Hawking radiation in our channel's search window for an unreasonably deep dive into all of that. And moving on to quintessence, Max White asks that if it is found that quintessence evolves over time, would our estimate for the age of the universe be wrong? Yes, it very much would. So changing quintessence means changing the strength of dark energy, which means changing the rate of accelerating expansion. The current age estimate of 13.7 billion years assumes a constant dark energy. If dark energy has gotten stronger, then the universe would be older because it would have been expanding more slowly in the past than expected. On the other hand, if dark energy has weakened, then the universe might be younger than expected. But none of this is by a lot. I would guess that we're still within plus or minus a billion years of the right answer. Jeffrey Giaffi asks whether quintessence being a scalar field could allow it to interact with the Higgs field and modify each other's expectation value. Well, the answer is absolutely, although we don't need them to be scalar fields to interact. If you dig through the literature, you'll find various studies about coupling the Higgs field to a quintessence-like field for various reasons. For example, apparently you can do this to eliminate the so-called Higgs instability, which blows up the Higgs field at high energies. Others use this coupling to explain dark energy and dark matter. There are lots of ways these fields could behave. The challenge is placing any experimental constraints on that behavior. Speaking of which, Marek Zilberman asks whether a particle of the quintessence field could account for dark matter. That's a really great question, and I have no idea. Quintessence would need to be coupled strongly with the Higgs field to give that particle enough mass, but it would still need to couple extremely weakly with the other fields to keep it from having been detected. I bet there are ideas out there to manage this, but I don't know how plausible they are. But I do want to take this opportunity to caution you. Where there are two mysterious things that we don't understand, there's a real allure to trying to make them the same thing. That might work sometimes, but more often it doesn't. So don't get caught in the same trap as the proponents of theories of quantum consciousness, or that aliens built the pyramids, or that Elvis shot JFK, because everyone knows that dark matter shot JFK.